When you look up at the night sky, you see a random scattering of stars, a beautiful, chaotic spray of light against an infinite black canvas. For all of human history, this is how we've seen the universe, as a vast, dark emptiness dotted with islands of light we call galaxies. But what if this impression of randomness is just an illusion, a trick of our limited perspective? What if the universe has a hidden architecture, a colossal, invisible web connecting everything across billions of light years? And what if the launch and deployment of the James Webb Space Telescope marked a turning point, finally allowing us to see it? As the scientific successor to Hubble, Webb brought with it a suite of new technologies capable of peering farther into the universe than any observatory before. It has now completed its most ambitious project yet, mapping a vast region of space and cataloging nearly 800,000 galaxies in a single panorama. And these revelations aren't just aesthetically magnificent, they carry immense scientific weight. What Webb found doesn't just fill in details, it's reshaping our comprehension of space, time, and cosmic evolution. The universe is not random, it has a structure, and seeing it for the first time is forcing us to confront a series of shocking new realities. To understand just how profound this discovery is, we first have to remember how we used to see the universe. For decades, our best view came from the venerable Hubble Space Telescope. In 1995, astronomers pointed Hubble at a seemingly empty patch of sky in the constellation Ursa Major, opened the shutter, and let the light trickle in for over 100 hours. The result was the famous Hubble Deep Field, and it was revolutionary. That tiny, dark patch, no bigger than a grain of sand held at arm's length, was revealed to be teeming with thousands of galaxies. Subsequent deep fields pushed even further, showing us a universe far more crowded than we had ever imagined. But these images, as incredible as they were, had a fundamental limitation. They were like looking at a sprawling city through a keyhole. You could see the lights and the activity, but you couldn't see the underlying infrastructure that makes a city a city. We saw the galaxies, but not the cosmic environment they lived in. Cosmologists had long theorized that such an infrastructure existed. They called it the cosmic web. Computer simulations predicted that all matter in the universe, both the normal matter we see and the mysterious dark matter we can't, should arrange itself into this structure. It would be made of long, thin filaments of gas and galaxies stretching across the cosmos and intersecting at dense knots, like great cosmic cities. In between would be vast voids where almost nothing exists. It was a beautiful theory that explained how the universe evolved from the smooth plasma of the Big Bang into the structured cosmos we see today. But it was still just that, a theory, a simulation. We lacked a telescope powerful enough to zoom out and see the grand pattern. The problem was light itself. As the universe expands, light from the most ancient objects gets stretched into the infrared spectrum. Hubble, primarily a visible light telescope, found its view obscured. To see the true architecture of the universe, we needed a new kind of eye. An eye with a mirror more than 6 times larger than Hubble's, attuned to the infrared. We needed the James Webb Space Telescope. In its first year, Webb embarked on its largest program yet, COSMOS-Webb. Led by a team of nearly 50 researchers, it dedicated over 250 hours of observation time to a single goal, to map a huge, contiguous patch of the sky deeper than ever before. The target was a well-studied region known as the COSMOS field. While Hubble's deepest views were tiny pinpricks, the area Webb mapped for Cosmos Webb is vast, covering a patch of sky about the size of 3 full moons. The result, stitched together from over 10,000 individual exposures, is the largest and most detailed map of the universe ever created. And looking at it is humbling. Where Hubble saw thousands of galaxies, Webb's new map has catalogued nearly 800,000. Almost every point of light isn't a single star, but an entire galaxy. But more importantly, for the first time, we can see the context. We can see the structure. The cosmic web is no longer a simulation, it's a reality. The map reveals the universe's grand design in stunning detail. We can see the long filaments of galaxies, tracing lines across the darkness. We can see where they intersect, creating crowded superclusters. And we can see the staggering emptiness of the voids. It's an image that stretches across space and back in time to within a few 100 million years of the Big Bang. This gives astronomers the power to study how a galaxy's environment shapes its evolution. But as this fire hose of data began to pour in, it immediately started creating problems. The map was beautiful, but what it contained was, in some cases, simply impossible according to our models. The universe Webb revealed is not the one we were expecting. If your mind is already spinning at the thought that the universe is far more complex than we ever predicted, do us a favor and smash that subscribe button. The discoveries coming from Webb are rewriting our cosmic story in real time, and you won't want to miss what comes next. The first major shock came from the sheer number of galaxies in the early universe. Our standard model of cosmology makes specific predictions about how galaxies form. The story begins with the Big Bang, creating an almost perfectly smooth universe. Over hundreds of millions of years, gravity would slowly pull matter together into small clumps, which would gradually ignite to form the first small, primitive galaxies. The key word here is gradual. The process was supposed to be slow. Astronomers expected the first 500 million years to be relatively empty. Webb shattered that expectation. In the earliest epochs, Webb found up to 10 times more galaxies than predicted. This wasn't a small error. It suggested a fundamental misunderstanding of how quickly the universe got up and running. It's like an archaeologist expecting to find a few mud huts and instead uncovering a sprawling metropolis. The dawn of the cosmos was far more crowded and far more brilliant than we ever thought possible. This discovery alone forced scientists to rethink theories about how quickly matter can coalesce. Webb provided spectroscopic confirmation for some of the most distant objects ever seen, like JADESGSZ 140, which existed less than 300 million years after the Big Bang. Finding such a bright and well-formed galaxy so early has profound implications. It suggests the process of galaxy formation was not slow, but rapid and incredibly efficient. This isn't just a new record. It's a direct challenge to the standard model. As if a crowded dawn wasn't enough, a second shockwave emerged from the data. It wasn't just about the number of early galaxies, it was about their size. According to the gradual formation model, the first galaxies should have been small. Massive galaxies like our own Milky Way should take billions of years to assemble through mergers. Finding a massive galaxy in the early universe would be like finding a fully grown oak tree a week after planting the acorn. And yet, Webb is finding a forest of impossible oak trees. The data has revealed ultra-massive galaxies, nearly the size of our modern-day Milky Way, within the first billion years of cosmic time. This discovery directly contradicts the gradual assembly model. To form these giants so quickly, star formation must have been wildly more efficient than our models allowed. Moreover, peering into the hearts of these ancient galaxies, Webb made another startling detection. Supermassive black holes, weighing millions or billions of times the mass of our Sun. How could such massive entities form so early? Their existence challenged conventional timelines and hinted at unknown mechanisms of rapid mass accumulation, with some scientists now theorizing about exotic physics like the direct collapse of enormous gas clouds to explain them. So now we have two interconnected, impossible discoveries. A universe with far more galaxies than expected, and many of them far more massive and mature than they should be. It challenges everything we thought we knew about galaxy formation and evolution. While rewriting the story of the early universe, Webb was also tasked with solving one of the biggest paradoxes in modern cosmology: the Hubble tension. For years, there have been two main ways to measure how fast our universe is expanding. The first method looks at the early universe, using the afterglow of the Big Bang to predict what the expansion rate should be today. This gives a value of around 67 kilometers per second per megaparsec. The second method measures the local universe directly, looking at stars in nearby galaxies. This method, pioneered by Hubble, consistently gives a higher value, around 73. Many thought this tension was a measurement error. One of Webb's missions was to use its superior vision to remeasure the local universe with unprecedented precision and settle the debate. The results are in, and they only deepen the mystery. Webb's new, hyper-precise measurements confirmed the local expansion rate is indeed higher. The verdict? Hubble was right. This is a monumental finding. It effectively rules out measurement error as the cause. The discrepancy is real. The universe is expanding faster today than our best models predict. This points to a fundamental gap in our understanding of the cosmos, suggesting our standard model of cosmology is incomplete. By trying to solve the Hubble tension, Webb has instead solidified it into a major crisis in modern science. What we are witnessing is not a series of isolated puzzles. It's a cascade of discoveries all pointing in the same direction. First, Cosmos Webb reveals the intricate structure of the cosmic web, but within that structure, the dawn of the universe is far too crowded. Second, we find impossible galaxies, far too massive, far too early, with supermassive black holes that grew far too fast. Third, the Hubble tension is confirmed, proving the universe is expanding faster than our models can explain. Individually, each finding is a landmark. Together, they represent a potential revolution. They tell us our standard model is missing major pieces. Scientists are now scrambling to figure out what new physics could explain these anomalies. Could dark energy be evolving? Is the nature of dark matter different than we assume? Or could it require revising our understanding of gravity itself? Webb's mission is far from over. It is continuing to probe ever deeper into the cosmos. Each new observation adds another piece to this bewildering, exhilarating new picture. Webb didn't just answer questions, it formulated entirely new ones. The title of this video is "We Are So Small." And standing before this map of 800,000 galaxies, it's impossible to feel otherwise. Each point of light is a city of suns, interconnected in a structure so vast it defies comprehension. It's a scale that can feel crushing. But perhaps the most humbling consequence of Webb's discoveries is the recontextualization of our place in it all. The fact that we, a species on a tiny blue dot, can build a machine capable of looking back 13.5 billion years to witness the dawn of creation is nothing short of miraculous. We can map the invisible architecture of the cosmos. That is not insignificant. It is a testament to the power of human curiosity and our relentless desire to understand our place in the universe. Webb has not given us all the answers. It has done something far more important. It has shown us that our questions were not big enough. It has broken our old models and opened the door to a new era of cosmology, one filled with deeper mysteries and more profound questions. We may be small, but in our quest for knowledge, in our ability to reach out and touch the very beginning of time, we are giants. The search has only just begun. What do you think is the biggest implication of these discoveries? Is there a flaw in our understanding of dark matter? Or is something entirely new needed to explain our universe? Let us know your theories in the comments below. And for more journeys to the edge of what we know, make sure you are subscribed. Thanks for watching.